so I'm starting to record. I will plan on having your tests graded by Monday. So I'm going to spend the next couple days mostly focusing on getting these lectures out of the way in Chapter 7, but over the weekend I'm going to be able to spend a lot of time on grading the tests, so you should have those back by Monday and we can discuss things. And the final is coming up next week. I think it's actually a week from yesterday, so that's kind of rough that y'all have a test a week more or less, but it's a very compressed schedule, so that's what it is. Any questions before I get started? All right. If there are no questions, then let me begin. So the point that we were at last time, so on Tuesday, we essentially boiled down all of our discussion to asking about the following systems. Of equations. Essentially, we are looking for things like x1 prime is equal to p11 of t x1 plus p12 of t x2 plus all the way up through plus p1n of t xn plus maybe a g1 of t, all the way down to xn prime, which is equal to pn1 of t x1 all the way up through pnn of t xn plus gn prime, or plus gnt. And as I mentioned, so first of all, this system is called homogeneous if all the GIs are 0. And another important fact to notice is that this setup is starting to look very, very much like it is going to be amenable to matrix mechanics, because this linear system, or this collection of linear differential equations, is pretty much completely determined by the data of these particular functions, the Pij, and possibly the GLs if the G's are not all 0. Any questions or any recollections just about this this place where we landed last time? So what I want to think about here is I want to take this problem that we're considering, and we're essentially going to do a bunch of matrix mechanics. And I want you to remember that associated to this particular problem, we can essentially be thinking about a matrix associated to P11 of t all the way up through P1n of t, down to Pn1 of t through Pnn of t. So this is a matrix. Now, admittedly, currently this is a matrix with values in functions of t, but as you might expect from our previous work, we can do most things explicitly in linear, like higher order linear equations, precisely when the coefficients are just numbers, or when they're constant functions of t. So you should kind of expect the same thing. You should expect for us to be able to go the furthest when this big system of first order linear differential equations shakes out to be a bunch of number coefficients in front of all the xj's in each point. And then this passage from this linear system of first order equations is literally determined by an actual matrix with number values, right? Okay. So it's for this reason that we now need to study matrices. So I want to essentially be going through an overview of matrices. How many people have seen some linear algebra, or at least are familiar with some matrix mechanics, like transposes and like uh, determinants, not just of 2 by 2 or 3 by 3, but more general stuff?
I've taken linear.
Okay.
I'm not familiar with any of that.
Okay. So we're going to start going through some matrix stuff. Okay, the first thing that I want to do is to reinforce something a little more general than just matrices. So I'm going to give the following definition. A vector space V over R or C is a set V. So here, there's a little bit of notational confusion writing V both for the vector space and the set, but that's fine. Such that for all V1 and V2 inside V, we have V1 plus V2 is also in V, so I can add vectors together. And K V is also inside V. Here, this is for any little vector V. I'm saying KV is inside the vector space for all K in R or C. So this is saying that I can scalar multiply my vectors. If I have a vector space over R, then I can multiply a vector by any real number and still have a vector in the vector space. And if it's a vector space over C, I can multiply V by any complex number and still have it land in the vector space with a bunch of rules. For instance, we have a 0 vector. So this means that any vector has a negative. So I can always have V plus -1 times V is equal to 0, the 0 vector. Maybe I'll write a little underline underneath the 0 to denote the 0 vector. And then we have a bunch of properties like how do we multiply? Like K of V1 plus V2 is equal to KV1 plus KV2. And similarly, K1 plus K2 on V is equal to K1V plus K2V. I haven't written the complete list, but hopefully this is giving you some sense for what a vector space is. It's a collection of vectors that you can add together and you can multiply them by scalars that satisfy all the compatibilities that you'd expect them to satisfy. Yeah. This isn't a very thorough definition, but I didn't want to just write down a bunch of properties that are a little stale. But at least I want us to be able to discuss what a vector space ought to be. Okay, so I want to this next discussion isn't necessarily as rigorous as I would want it to be, but this isn't a linear algebra class. So let me say the following. So inside a vector space, we can think of lines as K times V1, where V1 is not equal to 0. So I think of a vector space as, or at least inside a vector space, anytime I take a non-zero vector, I can take the line spanned by that vector, which means you multiply that vector by all of the constants that are in your arsenal. If we're over R, then you take the R span, or if you look at a vector space over C, you take the C span. So in particular, let's work with a two-dimensional vector space at the moment. if I am thinking of a vector, a non-zero vector in here, and that's given by 2 coordinates, say 1, 0, or 1, 2. 1, 2 will give me some non-zero vector inside this vector space. Here, this is R cross R. And you already know how to add vectors in R cross R, and you also know how to multiply them by constants. The line spanned by the vector 1, 2 is kind of a very natural thing. It's the line joining the 0 point to the vector 1, 2 and everything through it, right? And this is naturally associated with all of the products of a number times 1, 2. For instance, the 0 point is equal to 0 times the vector 1, 2. There's going to be a point over here called -1, -2, which is just equal to -1 times the vector 1, 2. So do you see how I can produce lines inside of a vector space by taking all of the scalar multiples of a single non-zero vector?
Yeah.
Okay. So now I want to just introduce the notion of a linear transformation. So this is all rather shaky and not the amount of rigor that I'd like to do, but really I would like for you to ask me questions if there's anything that's unclear about the ideas or the kind of overall visual picture that I'm trying to sketch for you. So the definition of a linear transformation is as follows. So let's have F mapping from V to W. So V and W are vector spaces. So F will be a function. So first of all, remember that V and W have sets underneath them. They're basically sets with additional structure. So first of all, a linear transformation should be a function from the set V to the set W. F is a function from the set V to the set W, which respects the vector space structure. So what does it mean to respect the vector space structure? That means the following thing. That means that if I take a sum of two vectors, if I'm looking at f of v1 plus v2, this should be equal to f of v1 plus f of v2, right? So what I'm saying here is that I can take, maybe let me draw pictures here. I'll just be drawing two-dimensional pictures, but so this is saying that if I have some vector v1 and I have some vector v2, and then I have some linear transformation to some other vector space. So here's v and here's w. The point is that whatever this function does to v1, say it sends v1 to here, this is f of v1, and say it sends v2 to this vector here, f of v2. Once you know what the function does to v1 and v2 individually, that forces what it does to v1 plus v2. So here the sum of v1 plus v2 is up here. And here, what I'm saying is that f of v1 plus v2 must be over here. Namely, this is the vector that I got by adding these two vectors. the function has to send this vector to the sum of f of v1 and f of v2. And similarly, f of kv has to be equal to k times f of v. So in pictures, essentially this one means that if I start off with some vector and I have, say, 3 times this vector, here's 3v. Well, then let's say this linear transformation sends this vector v to some vector over here. Here's f of v. Well, then 3v, f has to send 3v to 3 times this vector. Here's f of 3v, and it has to be equal to 3 times f of v. So one way to think about, or one way to kind of visualize or imagine what a linear transformation is that it has to send lines to lines, more or less. Like this line spanned by v has to be sent to a line spanned by the image of v, namely f of v. So if I take this whole line, in this case, if f of v goes here, it's going to be sent to this whole line. There's one exception to the rule that lines have to be sent to lines, because I could have f of v be equal to 0, in which case this whole line would have to map to 0. So here's an example of such a linear transformation. Let's say here is r cross r. I am able to make a linear transformation, which is called projection. So here's f, mapping to a one-dimensional space, r cross r mapping to r. And what this does is this is a linear transformation which essentially collapses all of the vertical components. So in actual coordinates, this linear transformation takes the vector a comma b and just maps it to a. So you can check that this is a linear transformation, namely this is, it satisfies these two properties. Where you send a sum of vectors is equal to the sum of where you sent the vectors. And it also respects this property. But I just want to point out that in this case, all of the vertical lines have been collapsed to points, more or less. What I'm doing here is I'm not being very rigorous, but I'm just trying to give you the idea of what you should expect from linear transformations. You should expect them to send lines to lines or send lines to 0, where every time I say line, I mean a line passing through the origin. Is this okay?
So where is the vector in f of v equals 0 in that left diagram?
So what this is let's take any vector. So let's actually make some computations, all right? So this map would send the vector 1, 1, which I draw here as 1, 1. Where would this vector go?
Just 1?
Yeah, this vector would go to just 1. 1. Okay?
Okay, gotcha.
What about the vector 1, 2? Where would this vector go?
Just 1 again.
It would also go to just 1. How about the vector 0, 1?
It would go to 0.
It would go to 0. How about the vector 0, 2?
0.
Also go to 0. So you see that what I have done is I've kind of collapsed this whole line onto the 0 point. And then, since all of these vectors, like 1, 2, so let me maybe write this out. The vector 1, comma 2 is equal to the sum of the vector 1, comma 0 plus 2 times the vector 0, comma 1, right? This is kind of writing this vector as one of these vectors and then two of these vectors. Is this okay?
Yeah.
What does the linear transformation do to the vector 0, 1?
0.
It sends it to 0. So this sum of 1, comma 0 plus 2 times the 0, 1 vector just maps to, so under f, this maps to the vector 1 plus 2 times 0, which is exactly what you see. This vector 1, comma 2 just gets mapped to the vector 1.
Okay, that makes sense.
Any other questions on these pictures that I'm drawing?
I'm just making sure. So the transformation here is that we like lost a dimension, right?
That's correct. A dimension has been lost here.
Thank you.
Yes, that's a very good point. Any other questions with what I'm writing up here? Any others? Okay, let me write down the following notion. So this is just kind of a heuristic. Matrices represent linear transformations. And what I mean by that is the following. And there's so much that I want to say that I can't really say rigorously. So I'm kind of frustrated with how I'm laying out these lectures. But what you need to do essentially is choose what's called a basis of your vector spaces. And once you've chosen a basis of your vector space, then the notion of matrices representing linear transformations becomes more clear. Let's try to write out the exact example that I just wrote. So inside this vector space R cross R, I can choose a basis, and I'll call it E1 is equal to 1, comma 0, and E2 is equal to 0, comma 1. So here, this is the vector E1, and this is the vector E2. E1 is stepping one step along the x-coordinate, E2 is stepping one step along the y-coordinate. And we know, since these two vectors are linearly independent, right? We know that these vectors are linearly independent. Yes? Yeah. Since these two vectors are linearly independent, and since there are two of them inside a two-dimensional space, any vector inside R cross R can be written as a suitable linear combination of these two vectors. This is just what's called Cartesian coordinates, right? Any vector A comma B is just exactly equal to A times E1 plus B times E2, which is A comma 0 plus 0 comma B, right? I'm just saying any vector in R cross R can be written as taking a certain number of steps along the x-axis and then a certain number of steps along the y-axis. Is this okay?
Yeah.
Okay. I'm afraid I'm about to do a very bad lecture. Okay, so what I want to do is I want to show you some way in which a matrix can represent the linear transformation that we want. So the linear transformation that we want here is, sorry, I want to map this to R. And I can specify what I want my linear transformation to do by specifying what it does on a basis. So in particular, I'm going to say the linear transformation that I want sends E1 is going to map to, let me write a vector here, E1 prime. So here is the 0 coordinate of the vector space R, and here's E1 prime inside R, which is just the vector 1. So E1 is going to map to E1 prime, and E2 is going to map to 0. So this is precisely what I was showing you in this last picture. What happens is that any point, A comma B, just gets sent to A, the length A. Right? You essentially forget about the second coordinate. You're projecting it down onto the real line spanned by E1. Okay?
Yep.
What I want to show you is that I can write a matrix. This matrix is going to be the matrix 1, 0, 0, 0. And I can teach you how to multiply vectors by matrices. So the idea is that if I have some V1 and V2, this matrix is supposed to tell me how I go from the point V1 and V2 over here to somewhere over here. And the way that this goes through is I multiply matrices. This thing, the recipe is, this is going to be the vector V1 times 1 plus V2 times 0. And then down here, it's going to be V1 times 0 plus V2 times 0. Has everyone seen how we multiply a vector by a matrix in this fashion? Or is this new?
Maybe a quick reminder.
Okay, yes. I will do a quick reminder in just a bit. But the point is that we should check what this does on our particular basis elements. So 1, 0, 0, 0 times the vector 1, comma 0 is equal to 1 times 1 plus 0 times 0, and then 1 times 0 plus 0 times 0, which is equal to 1, 0. And we should check what this does on our other vector, 0, 1. This is going to be equal to 0 times 1 plus 1 times 0, and then 0 times 0 plus 0 times 1, which is equal to 0, 0, or the 0 vector. So, okay. If you haven't seen matrix multiplication of vectors before, maybe this is very confusing. But the fundamental thing that I want to draw your attention to is that in some way, this matrix is encapsulating this linear transformation of projecting from this two-dimensional vector space R cross R to this one-dimensional vector space R. So I'll speak more about all the mechanics that are going on here, but in some way, this picture is saying matrices are how you describe a linear transformation. there are probably many questions, but do you have any questions that I could try to answer about this picture?
No, I think I get what you're saying.
Okay, that is all that I'm asking for on this kind of heuristic piece. I'm just trying to instill in y'all like how to try to think about linear transformations and matrices. And it's okay if things are not very clear at the moment, because I'm about to do a bunch of definitions. Okay, so now formally, a matrix. So a matrix is an m by n array of numbers. So the m, if I say m by n, that means that there are m rows and n columns. And then the array is listed by putting, if this is the matrix A, then I'll write little a, and then I'll write the numbers underneath, where the first number refers to the row and the second refers to the column. So A11 is in row 1 and column 1. And A21, or sorry, 1, 2, is in row 1 and column 2. A21 is right here, so it's in row 2 and column 1. A22 is over here. All the way down here, I've got AM1. Over here, I've got A1 comma n, and all the way down here, I've got AMN. Okay. This is probably not too new, but this is written as the matrix Aij. So I could say A is this matrix, and I could also write this, which tells you what each of the Aij's should be. Any question on this notation? Okay. So associated to a given matrix A, we also have the transpose. So define a new matrix. A transpose, which we interchange the rows and columns. In particular, if we start off with an m by n matrix, we'll end up with an n by m matrix. So if I start off with A being the matrix 1, 2, 5, 7, what is the transpose? A transpose is equal to what? Well, this first row will become the first column, so 1, 2. And this second row will become the second column, so this is 5, 7. You see that I've essentially flipped over the main diagonal. The diagonal entries stay the same, but the off-diagonal entries end up being flipped. That's how you can think of the transpose for square matrices, but of course not all matrices need to be square. So if I have the matrix 1, 3, 5, and 2, 4, 7, then the transpose, A transpose, is going to be equal to, well, I just switch or flip, not both, the columns and rows. So now the first row, 1, 3, 5 of A, becomes the first column of AT, transpose of A, 1, 3, 5. And the second row becomes the second column. Okay? Any questions about this? No? Okay. Another definition is that we can conjugate all the elements in A. So if A is a matrix with complex numbers, entries, then A bar is the matrix where each entry has been complex conjugated. So in particular, if I start off with the matrix, say 1, I, negative I, 1, then what will A bar be equal to?
One negative I1.
Mm-hmm. Yep, all I've done is I've complex conjugated all of the terms in here. If A is a matrix with all real coefficients or all real entries, what is A bar?
The same as A.
Exactly, exactly. Right? If you have a bunch of real numbers, then the complex conjugate doesn't change a real number, it just fixes it. So this is a way that you can write whether a matrix has real entries. A matrix has all real entries if A bar is equal to A. And then we'll make this definition, and it'll be a little useful. Combining both of these operations, combining these both operations, so taking the transpose and then taking the conjugate, is equal to the adjoint of A. Adjoint matrix of A. So in particular, what's the adjoint of A? What is A bar T if A is equal to 1, I, negative I, 1?
Is it just the same thing?
Yeah, it's just itself. Right? We already, first of all, we can take the transpose and the conjugate in any order so that A T bar is the same thing as A bar T. So we already computed A bar up here, and then doing the transpose just flips along the diagonal. Notice that most of the time, A bar T will not be equal to A. For instance, if I take the matrix 1, I, 0, for instance. This is some matrix that I can take, right? Now, the transpose conjugate will be equal to, or the adjoint will now be equal to 1, negative I, 0. So in general, a matrix and its adjoint are different. Questions here? No questions here. I know this feels very far from the differential equations that we were just doing and that you were just doing on your test yesterday, but this will all come back to help us solve, actually very easily solve systems of first order differential equations, because it's essentially just like solving linear systems, which is what we're headed for. Okay, so matrices do properties of matrices. First of all, matrices have a very rich structure. So the first thing is that we should mention when are two matrices equal. A and B matrices are equal if all of their entries are the same. And I'm going to write either 0 or 0 bar, perhaps, to denote the 0 matrix. Which is the same thing as the matrix where all of the entries are 0, right? That's a valid matrix. Okay, and now we can start talking about the structure on matrices. First of all, matrices can be added. So I can define A plus B if A and B are of the same, are both M cross N. As long as these two matrices are of the same rectangular shape, I'm allowed to add them. And so I get Aij plus Bij. This is the matrix, essentially. So A plus B is equal to the matrix Aij plus Bij. Does this notation make sense?
Yeah.
I'll just do an explicit example so you can see what's going on. 1, 2, 3, 4, 5, 6 plus, I don't know, negative 5, 10, 11, 1, 1, 1. Well, this matrix tells me I just add up the coordinates that are in the same position. So this is just going to be 1 plus negative 5 is negative 4, 2 plus 10 is 12, 3 plus 11 is 14, 4 plus 1 is 5, 6, 7, right? It's just telling me add up coordinate-wise. Any questions?
Yeah, where you say A plus B of, does that say of A comma B are both? What does that word say? At the very end?
If. So I'm not allowed to add matrices if they're of different shapes. So I can't pretend that I can add 1, 2 plus 1, 3, 5, 7, 9, 11. I am not allowed to add these types of matrices together.
Okay, so what's that last word at the end of that sentence?
Both M cross N.
Okay, thank you.
Right. M cross N is my way of denoting what the dimensions of the rectangle are. Okay. Matrices can be multiplied. By scalars. And what does this mean? That means if I take any scalar, either complex or real A times alpha is going to be equal to alpha Aij. Right? Does this notation make sense? What does this notation say that I've done?
You multiply every term or every entry by alpha?
Exactly. I multiply every entry by alpha. So the matrix negative 5, alpha is negative 5, and I'm taking the matrix 0, 4. Well, this recipe just tells me everything gets multiplied by negative 5. So this goes to 0, and this goes to negative 20. And they satisfy a whole bunch of compatibilities, like alpha times A plus B is equal to alpha of A plus alpha of B. And similarly, alpha plus beta of A is equal to alpha of A plus beta of A. Can someone tell me what structure I have just more or less put on matrices?
Similar to the vector space you talked about earlier?
Yeah, exactly. Matrices form a vector space. And it just depends, you demand what sort of numbers you're going to allow yourself to multiply by, but we can either write matrices as forming a vector space over R or as a vector space over C, right? I know how to add two vectors together, namely I can add two matrices of the same kind. So maybe I should write M by N. M by N matrices form a vector space. I have a zero matrix, such that when I add that zero matrix to any other matrix, I get back that other matrix. I can scalar multiply them, et cetera, et cetera. So matrices are maybe your first example of vector spaces that don't just look like Cartesian space. They kind of look like Cartesian space, but some big dimensional Cartesian space. Is this okay? Any questions? Okay. It turns out that there is an additional, very special structure that we can put on matrices that is more than a vector space. This is something that you cannot do in a random vector space, but you can do in matrices. Matrices can be multiplied. And let's write that. So A times B. And now here's where things become interesting. We are allowed to multiply matrices, can be defined if A is an M by N and B is an N by L. Matrix. So here already you're perhaps seeing that this multiplication is a little bit weird, or maybe it doesn't seem to really respect the vector space structure that we just put on it, because the vector spaces were for all M cross N. But if M is different from N, then I can't multiply an M cross N matrix by an M cross N matrix. Note, if M is not equal to N, I cannot multiply an M by N matrix and M by N matrix. And the matrix multiplication is defined as follows. A times B is going to be the matrix given by the coefficient Cij, where Cij is equal to the sum from k is equal to 1 all the way up to n of Aik Bkj. Okay, I have just written a disaster for you. It is impossible to tell what I have just done, but an example should clear things up right away. Let's do the example of a 3 by 2 matrix multiplied by a 2 by 4 matrix. So a 3 by 2 means I have 3 columns, or sorry, 3 rows, A11, and 2 columns, A12. Here I have A21, here I have A22, and here I have A31 and A32. Right? This is the most general 3 by 2 matrix that I can write. Is this okay?
Yeah.
That's a yes that I heard. Now I'm going to write the most general 2 by 4 matrix. It's going to have a B11 here, a B21 here, a B12 here, a B22 here, a B13 here, a B23, a B14, and a B24. That's okay? So the picture of matrix multiplication is I take columns here and I do the dot product with rows over here. So the first coefficient of C11. So first of all, what are the dimensions of the product matrix going to be?
3 by 4.
Yeah. Now I'm going to get a 3 by 4 matrix out of these two matrices. The first entry is going to be the dot product of the first column and the first row. So in other words, it'll be A11 times B11 plus A12 times B21. Right? Is this okay?
Yeah.
The entry in the 1, 2 position will be the first column dot product with the second row. So here it'll be B11, or sorry, let me write it as A21 B11 plus A22 B21. So to get the first thing, I paired these two. To get the next one down, I paired these two. To get the next one down, I'm going to pair these two. Next one's going to be A31 B11 plus A32 B21. Okay. What's going to be, so this is the C11, C12, C13 entry. What is going to be the C21 entry? Sorry, C12 entry.
A11 times B12
Exactly.
plus
A11 B12 plus
A12 B22.
Yep. So the C12 entry comes from the first row of the first matrix and the second column of the matrix. So the next one, C22, is going to come from the second row and the second column. So C22 is going to be A21 B12 and plus A22 B22. You start to see how this whole table gets filled out. I just take like the Cij is equal to the dot product of the ith row and the jth column. Is this okay? Any questions here? Should I do a real example with numbers?
Sure.
Yes.
Great. Okay. Actually, what I'm going to do is I'm going to make y'all do some examples with numbers, and I'm going to point out a very important fact. Matrix multiplication is not commutative. So I'm going to write two matrices. I'm going to have A being equal to 1, -2, 1, and 0, 2, -1, and 2, 1, 1. I'm going to have B being equal to 3, 1, 2, 1, -1, 0, and 2, -1, 1. And what I'm going to ask you to compute is both A times B and B times A. If matrix multiplication were commutative, then we would expect these two to always be the same matrix. But as long as I've chosen my example correctly, you'll see that these two matrices are different. So fundamentally, this is a new kind of multiplication that you probably have not seen before, because as far as I'm aware, all of the multiplication that you know how to do, namely inside R or inside C, those are commutative multiplications. But here we have a non-commutative multiplication. So why don't you compute these two? Cool. So just to check, let's do some of these. I'll do one of the computations really quick. So we have these matrices, then A times B, the first coordinate is going to be this row and this column dot producted together. So 3 minus 2 plus 2. So I get a 3 up here. The next one is going to be the dot product of the second row and the first column, namely 2 plus negative 2, so I get a 0 here. Now lastly, I'm going to have 6 plus 1 plus 2, which is 9. Then I'm going to do the whole thing over now with the first row and the second column. I get 1 plus 2 minus 1, which is 2. Here I get 1 times 0 plus negative 2 plus a 1, so this should be a negative 1. And then here I'm going to get a 2 minus 1 minus 1, so a 0. And then lastly, I'm going to do it for the same first row, last column. 2 plus 1 is 3. Negative 1 and 5. Did y'all get this for A times B?
Yes.
Did anyone get a different number in any of these entries and wants to ask me about it? Okay, B times A. Now I should probably write it so that I don't mess up disastrously. So B times A, I'm going to write as, I'm just going to write A again over here. 1, negative 2, 1, 0, 2, negative 1, and 2, 1, 1. And I write them this way, I have a less chance of messing up. I'm going to have 3, so B times A is, the first coordinate is going to be 3 plus 4, which is 7. The next coordinate is going to be 1. The third coordinate is going to be 2 plus 2, which is 4. The next one's going to be negative 6 plus 2 plus 2, so negative 2. The next coordinate is going to be negative 2 plus negative 2 plus 0, so negative 4. And the next coordinate is going to be negative 4 minus 2 plus 1, negative 5. And then the last one, I take the first row and the last column, 3 minus 1 plus 2, so that's 4. Then I get 1 plus 1 plus 0, so 2. And lastly, I get 2 plus 1 plus 1, so 4. Did anyone disagree with one of these numbers that I got? Did I do that too fast? Or are people feeling okay about this?
I think it's okay.
Okay. Okay, and here you immediately see that matrix multiplication is not commutative because I multiplied these two matrices, A and B, in different orders, and I got very different matrices. Right? So this is something that you must disabuse yourself of the notion that multiplication is always this commutative thing. Maybe this starts making more sense why, from a young age, you were always drilled in these, commutative, multiplication is commutative, and you're like, why? Of course, multiplication is commutative. Well, that's mentioned from very early on because at some point you're going to get to multiplications which are not commutative. Okay. Okay, yes. So now let me kind of tie this back in. Vectors can be thought of as either 1 by n or n by 1 matrices. So I want to bring up two things here. So first of all, we can write the dot product as a product. So write the dot product as a multiplication of matrices. Let's say that I have two vectors in the same 1 by, let's say, n by 1 family. So let's take 3 by 1 vectors. So I'll call one vector 1, 2, 3. It's called v1. And I'll call v2 equal to 100, 3, negative 4. So these are two vectors. And I can find the dot product v1 dot v2. Well, in this situation, I can write this as the matrix multiplication given by v1 transpose times v2. Because the transpose will make this matrix into a 1 by 3 matrix, namely 1, 2, 3. And then this one is just a regular matrix, 100, 3, negative 4. And what is the matrix multiplication of these two? It's a 1 by n times an n by 1 matrix. So I expect a 1 by 1 matrix, which is just a number. And that number is equal to
94.
Sure, you're faster than me. I was just going to write 100 times 1 plus 3 times 2 plus 3 times negative 4, which is exactly what the dot product is. So this is a 3. So first of all, matrix multiplication, in a certain sense, generalizes dot product, because if you think of your vectors as matrices, then you can write the dot product as a matrix product after taking the transpose of one of your matrices. The other important thing to remember is that if I have an n by n matrix times an n by 1 matrix, I expect back another n by 1 matrix, right? Because n by n multiplied by n by 1, I should take the outside numbers and get back an n by 1 matrix. So here, if I have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm multiplying it by the matrix slash vector 1, 1, 0, what do I get? Well, you know how to multiply matrices. I'm just going to tilt this column over and do dot products. So I get 1 plus 2 is 3. I get 4 plus 5 is 9. And I get 7 plus 8 is 15. This notion of matrix multiplication, where one of my matrices is an actual matrix and the other is a n by 1 matrix or a vector, is the idea of linear. This is how we get linear transformations. Because here I'm sending a vector to another vector, and the way that I'm sending it is via a matrix, so to speak. So now this earlier example that I did of 1, 0, 0, 0, well, what does this do on 1, 0?
Keeps it at 1, 0.
Yep, it just sends it to 1, 0. And what does this matrix 1, 0, 0, 0 do to 0, 1?
You get the 0 vector.
Yeah, it gets the 0 vector. So this is exactly the picture that I had. This is a mapping from R cross R to R cross R, in the sense that it's taking me from a two-dimensional vector space to a two-dimensional vector space. And what it's doing is it's just projecting down. So this sends each of these vertical lines just gets mapped to their point of intersection. And some vector out here gets mapped to the projection. This shouldn't be here. So this whole two-dimensional vector space gets mapped to this line. That's what this matrix is telling you to do on the level of vectors. You can compute. You put in any a comma b, you do the matrix multiplication, and you see what it tells you. In particular, just as I described, I have 1, 0, 0, 0, and I multiply, or I compute what this does to the vector AB, what do I get? What should the first coordinate be?
Just get A, 0.
I just get A here, and I get 0 here. In other words, I send the vector A, say this is 3, 4, to the vector 3, 0. Now is the connection between this matrix and this linear transformation becoming more clear? Yes or no? Okay, no one wants to say anything. That's all right. I don't mind. But seriously, are there any confusions based on the stuff that I'm talking about?
No, I think it's clear.
Great. I hope so. I'm trying. Okay. Now we're going to start really moving into only thinking about n by n. Well, no, that's not true. We're not only going to think about n by n matrices, but mostly we're going to think about n by n matrices. So square matrices. If we consider n by n matrices, we already know that there's one special matrix in the n by n matrices called the zero matrix, right? That seems reasonably special. It's special because it's the additive identity for the addition, right? If I add the zero matrix to any other matrix, I get back that other matrix. So obviously the zero matrix is playing an important role in the same way that zero is playing an important role in any number system. But we also have another very special matrix element, which is going to be called the identity. And this is going to be the matrix with ones along the diagonal. 1, 1, 1. Say this is in the identity in 5 cross 5. And all the rest are zeros. This is going to be the multiplicative identity. Id will be the multiplicative identity. So why don't you compute for me the multiplication of this matrix with A11, A12, A13, A21, A22, A23, and A3, sorry. Oh, I keep doing this backwards. I'm so sorry. A12, or A11, A21, A23, A12, A22, A32. Jesus. 3-1. It is a disaster what I'm doing here. 3, 2, and then A13, A23, and A33. What is the product of these two matrices? Well, what's the first coordinate?
A11.
Yep. What's the second coordinate?
It's just the identity
I
matrix.
feel like it's
A21. Third coordinate is going to be A31. Here it's going to be A12, A22, A32. Now I'm not even computing. This is the identity matrix in the sense that when you multiply this by any other matrix, it returns for you the matrix. So it deserves to be called the identity matrix. Right?
yeah, that makes sense.
So in other words, the matrix with ones along the diagonal and zeros everywhere else plays the role of the multiplicative identity. So when you multiply it by any matrix, it returns that other matrix. Okay. So we're like trying to build back up our intuition that we had over say the integers or the real numbers, the complex numbers. One thing that's getting in our way in a big way is that multiplication is not commutative. So let's write the following. A matrix A is called invertible if there exists a matrix B, and A has to be, well, let me just define it. Invertible if exists a matrix B. Let's call it M by M. Is called invertible if there exists a matrix B, which must also be M by M, such that A times B is equal to the identity on M. You can't see what I'm writing. Right, so this corresponds very nicely to our idea of what a multiplicative inverse ought to be, right? If you think about the rational numbers, the multiplicative inverse of a rational number is going to be precisely the number such that when you multiply them together, you get 1. And that's exactly what we're trying to recreate here. We're saying a matrix is going to be called invertible if I can find another matrix such that their product is going to be the identity. A matrix will be called singular or non-invertible if no such B exists. Anyone think up a real quick example of a non-invertible M by M matrix for me?
Sorry, I have a question.
Sure.
So does the B have to have the same rows and columns as A? Like
It has to have the same number of rows and columns, but it will almost never have the actual same rows and columns.
Okay, but like M equals M and N equals N.
Yeah, hopefully, this is just my terrible handwriting. I'm doing M by M matrices now.
Okay.
Can anyone think up an example of a singular or non-invertible M by M matrix?
A zero matrix?
Yes, very good. The zero matrix, call it 0 sub M by M matrix, is always singular. Because if I have an M by M matrix full of zeros, any dot product with a bunch of zeros will just give me 0. So the 0 M by M matrix, when multiplied by any other matrix, will always give me 0 back. It can never give me ones along the diagonal back. Does this make sense?
Yeah, that makes sense.
This corresponds exactly to the notion that in terms of numbers like Z or C or R, 0 is also not invertible. The number 0 can never be multiplied by another number to get 1. So this leads to things like saying you can't divide by 0 and stuff like that. The exact same thing is happening here. Okay, and now we're going to circle back to something that we have been brushing up against often in this course. How do we check if an M by M matrix is invertible or singular? Does anyone have the answer for me?
The determinant.
Yes, the determinant. Determinant is a beautiful, beautiful. So I'll just write it out. A matrix, a M by M matrix is invertible if and only if the determinant of A, that A, is not equal to 0. And what this means is that a matrix is singular if and only if the determinant is 0. Are y'all comfortable with computing higher determinants than just 2 by 2 or 3 by 3?
No.
No.
Okay. So the determinant of an M by M matrix is calculated via expanding minors. The idea is as follows. let's consider the situation in a 4x4 matrix. The idea is, let's start with the case of the first column. Oh, well, first let's discuss the idea of a minor. So we define the Mij minor to be the matrix when we delete the ith row and jth column. So if I do, I don't know, 1, 2, 3, 4, 10, 9, 8, 7, 6, 5, 4, 3, 1, 0, 0, 0, then the minor, the matrix minor associated to 2, 2 means I delete this column and I delete this row, and I'm left with a 3x3 matrix. So M 2, 2 is going to be the 3x3 matrix given by 1, 3, 4, 6, 4, 3, 1, 0, 0. Right? I've deleted the column and row passing through the given entry, and I get a smaller matrix by taking what remains and kind of collapsing it. Similarly, if I look for the 4, 4 minor, that means I'm going to delete the column 4 and I'm going to delete the row 4. So M 4, 4 is going to be equal to 1, 2, 3, 10, 9, 8, 6, 5, 4. Right? I've deleted these two columns and seen what matrix remains. Are we okay with the notion of a matrix minor?
Yeah.
Okay. So then the determinant can be computed by essentially summing up the matrix minors as follows. Det A is going to be equal to the sum of the Cij times summing from -1 I plus j of the Mij as we vary I goes from 0, well, 0 up to m. This is how we expand along a column. This is expanding along a column, or expanding along a row. And if we expand along a column, it's the sum of these, but now where j goes from 0 up to m. This maybe seems kind of opaque. So let me do an example in a 4x4 case. Do I have time? Yeah, I have 5 minutes. Okay. So example. Let me just actually write down what it will be for an explicit 4x4. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 0, 1, 0, 1, just some random matrix. Let me expand along the first row. So what I'm going to do is, and this should be kind of very reminiscent of how you calculate 3x3 determinants or 2x2 determinants. I'm going to start off with, if I expand along, so expand along first row, I'm going to start off with 1 that's the first term, times the matrix, the determinant of the matrix minor. So times det of M11. In this case, the determinant of this 3 by 3 matrix formed by deleting the first row and the first column. Now I'm going to do a -1 times, now I do the next minor, times 2 times determinant of the minor associated to 1, 2, plus 3 times the determinant of M13 plus a -1 times 4 times the determinant of 1, 4. So in other words, what I've just done is I've linked the computation of a determinant of a 4 by 4 matrix with a number of determinants of 3 by 3 matrices. And similarly, each 3 by 3 matrix, if you want to compute the determinants of a 3 by 3 matrix, this procedure breaks it down to computing a bunch of 2 by 2 matrices. Let's actually compute 1 times det M11. This is 1 times det of, I take the minor, 6, 7, 8, 10, 1, 2, 1, 0, 1. Right? This is the minor that I get from deleting the first column in the first row. And now I just repeat the procedure. What's the determinant of this? Once again, let me expand along the first row. It's going to be 6 times the determinant of 1, 2, 0, 1 minus 7 times the determinant of, here I do cofactor expansion of 10, 2, 1, 1, then plus 8 times the determinant of the cofactor 10, 1, 1, 0. Yeah.
For this example, would it have been better to expand along the bottom row?
Yes, definitely. But if you expand along the bottom row, you have to be cautious about how the signs change. So if we expanded along the bottom row, we'd start by a -1 times the determinant of the cofactor here, then a +1 times the determinant of the associated cofactor, then a -0 times this cofactor, and then a +1 times the determinant of this cofactor. So the point is that you can expand along any column or row, and you just have to keep track of some tricky signs when you do that. That's all.
Okay.
But perhaps if you would like to keep things simple, you can always compute determinants by expanding along the first row, and then you just switch positive, negative, as you do each next term. So I'm going to have a +1 times 1 times the determinant of the cofactor, plus a -1 times 2 times expansion of this cofactor, et cetera, et cetera, et cetera. It is 1 o'clock, but I'm happy to answer any questions or do another example here.
So it flips signs because of that -1 I plus j term. Right?
Yes, exactly. The
Okay.
-1, where did I put that? Yeah, this -1 I plus j term is what's telling you what the coefficient is. And if you always expand along the first row, then the first term will always be 1, 1. And so I've got -1 to the 2. So I always start with a +1. And then here, this will be the 1, 2 entry. So I'll have a negative. And then here, this will be 1, 3. So I'll have a positive again. Yeah, so this thing is what's controlling the flipping of the signs. Yeah, of course, other resources are very helpful for this. So I definitely recommend that you take a look at outside resources like Khan Academy. That'd be very good.
Thank you.
Sure. Any other questions on this? If there are no further questions, then have a nice afternoon.
Thank you. You too.
Thank you.
Yeah.